Brief about myself, I'm the founder of Activeloop. Was working on the company for the last 6 years. Before that, I was doing a PhD at Princeton dealing with petabyte scale datasets. And one of the challenges when we work with Fortune 500 customers and including startups is that when we enter, they have so many different databases, data warehouses, data lakes, all across different clouds. And it's very fragmented to be able to access this data. We're talking to a customer and there's a VP who had like different reporters. They're like in life science pharma, they have manufacturing business, and they produce a lot of drugs. And there's a simple question, what is my last month revenue? He asked, and they got 3 different answers from different tables across their organization. And the challenge is not only in this big, large organization, but also across many different startups as well, where you have all these different data sources coming from different places and you need to unify and answer a question, but answering the question itself has a lot of contradictions themselves. What if we can actually connect AI to all your data to be able to answer any question, but in a secure and enterprise manner, where it can understand your domain-specific language and answer instantly the question without going through the business intelligence group and going through a bunch of bureaucracy to bring you the answer. And today, I'm going to actually show you both a demo and also how you can build this yourself as developers using DeepLake. So here's a demo. What we are asking here, can you summarize me recent breakthroughs in brain edema research? What we did behind the scenes, we have 2 datasets. One of them is OpenAlex, which is about 130 million all published article datasets by scientific community. And another dataset that sits on top of Azure is 1.3 million radiology images. This question is very simple. Think of Perplexity. You get the answers, get the citations, and here you go. But what if we can ask a question that needs to cross over 2 different datasets? And here in the example, what it does, it both searches in the OpenAlex dataset and in RAD ImageNet dataset and brings back an answer, validating it every step by not only just giving you citations, but also searching across the images and bringing them as a citation inside the text. And furthermore, what if we go and ask another question? How do these breakthroughs in research apply to my patient data? Imagine I'm in a hospital. I have a lot of patient reports. I want to upload and see, well, how does these patient reports actually correspond to the scientific community and research? And here is a simple, I already have prepared kind of PDFs that I drag and drop. But the big difference was happening behind the scenes, and we'll look into the technology behind that. There's no any OCR pipeline. This is directly processed by visual language models that take the embeddings or bag of embeddings in this case, now compare against the database you already have and bring the final answer that summarizes both the textual scientific articles from 130 million research papers, but also the images and also the patient data. And this is like a kind of a proof of concept to showcase how you can build so-called rugs, but across not just a single data source, across all the data sources you have. So let's talk about the technology that enables this. So we open source DeepLake about 4 years ago. And so far we got about 2.6 million downloads, 8.2 now thousand GitHub stars, 3,000 open source projects, depending on it. Technically speaking, this is the most popular data lake on GitHub that's specialized for AI. But furthermore, we also have enterprise customers, including Fortune 500, that deploy this and manages all their multimodal data currently in production. And what we released about a month ago is DeepLake version 4. And I'll tell you about that in a bit. So let's take a step back and focus about database theory. When Oracle released their initial database, all the index, all the data is in memory. It works great. You have this low latency, hot memory access. You can ask a lot of questions or queries, SQL queries, and get response back. Then people realize as the data grew, keeping everything in memory is very expensive. Why don't we actually offload some of it into the local disk? And with this, you can optimize the cost by 70% by having the data laid out on a local disk file system and then have the index in memory so you can ask the questions. And then That's where data warehouses came in, including Snowflakes or Databricks, where they said, hey, what if we do this compute and storage isolation where we can take the data and put it on object storage and still keep run the compute on this dynamic cluster where you can shut it down whenever you want. And then by this, we can now scale even further the data, order of billions of rows, and run the queries up to 5 times cheaper. But is there anything that we can do further? Can we actually take the index and also store it on object storage and cut the cost another 2 times? And in total, if you look by 10 times. This hasn't been possible before, but we make it work. And introducing DeepLake version 4. And what it does, it actually brings 10 times faster ingestion under a second queries or 250 million vectors, everything sitting on top of an object storage without any in-memory cache, with 25 Gbps streaming from the storage layer to the computing machines. And all this multimodal, simple, no cache, async, and concurrent. Now, let me give you kind of try to ramp you up on AI search. How many of you built a RAG here? 1, 2, 3, 4, 5, 10. I guess we have more people here as well. How many of you done lexical search? Vector search? Hybrid search? Agentic search? There's a bunch of other acronyms I know, but I won't share here. But basically, if you think of this letter here, is that you start with simple lexical search. Think of this like an early version of Google where you type your keywords, and then you bring across all the data set the keyword matches and bring back the results. Later, what happened 2 years ago successfully, that large language model representation became so good that it started kind of outpacing the BM25 index, this embedded index for you that you use behind the scenes for the keyword search, and had semantic meaning inside that improved the results. And furthermore, you not only now have top 10 links, but also get this top 10 links and give this to an LLM and get a final answer. Then you now can build your compound systems, building the agentic search itself. And then you can use multiple kind of iterations to refine your search, maybe verify the result, maybe also run a text to SQL and bring the results. But where is this going all? And the next step, which is not yet kind of is in research mode, is building end-to-end neural search systems. And think of the self-driving cars. Recently, Tesla replaced all their 300,000 lines of C++ code that does the planning on driving the car with a neural network. And what if you can do end-to-end neural network search altogether? So what is RAG? It's just a fancy name for enterprise search. You have a bunch of documents. You take these documents, parse them through an OCR pipeline, cut into small pieces, vectorize, store it in a vector database, pick any of your favorite vector database. Then whenever there's a query, you fetch the top 10 results, similar, bring them into the context, ask the query to the LLM and get the answer. All this looks simple. Everyone, you did it at home. But a question here. How much complexity is it to build your own version of Google? Here's a recent research post by Mario, who actually went and studied Google and all the legal work they have done in the past to kind of reverse engineer what is the search engine complex system behind the scenes that they spend order of billions of dollars building themselves. And then since we are in developer system, like meetup today, I can actually deep dive on this architecture a bit. So on the left, you see on the top left, you see the crawler that collects a lot of the data. It takes the kind of the lexical part, put that into an inverted index, which they call this word index here. And then they also crawl separately the images, put them into an image container, and all this looks great. And then whenever you run a query, it gives the top 1,000 results and then brings to this bunch of, is what they call Mustang, as bunch of re-rankers, including DeepRank or RankBrain, that now use neural networks to be able to re-rank the top 10 results and bring it back to you. But also before bringing back to you, there's also this twiddlers that they can build a lot of manual this feature engineered kind of priorities or repriorities based on time of events, what's happening in the world, to kind of reprioritize what you see and personalize and eventually bring it back to your Google search result, all this in milliseconds. So all these RAG builders, what do you think, how much time it will take us to build this and how much infrastructure? It's pretty complex system. But what I think is what happened recently is because of, thanks to the deep learning, is that there's a crack in the system whole the process. And what this can be actually replaced by end-to-end neural networks. And the system here, what we are proposing with AI search with DeepLake version 4, that actually can cut the cost by 10x, is running the search across multiple data sources, multiple clouds, multiple storages. But also this key last component, which I will go through the code in a bit, is that now you can take PDFs instead of writing your own OCR pipeline, separating the images with text. You pass this through ColPali, which is another deep learning model that takes the image, gives a bag of representation, run the search, and bring back the final results into an LLM that can give you a summary. And one of the key things that we did is that we took this index from the compute layer and put it on object storage that can save the cost by up to 10 times when you run the queries. However, now you pay outside of a latency cost, where instead of millisecond latency, you run the queries under a second. For real-time use cases, it's not great, but for data warehouse style or analyst style queries, this works pretty fine, especially the savings you have. But the problem here, going from an embedding to bag of embeddings, which is this dense representation of multimodal data that recently surpassed like this kind of classical pipelines, requires 30 times more storage. And you can actually trade off this 10x cost efficiency with 30x kind of the trade-off, and now get these multimodal capabilities to run search across all your data sources without writing all these manual pipelines. And now let's go through kind of the use case step by step building this. We just really recently revamped our docs, so you can go to DeepLake.ai to docs.deeplake.ai, and there's a RAG guide, and which guides you to go from building just a simple lexical search to running this multimodal DeepLake search that I mentioned in a bit. Here you pip install DeepLake, you load a dataset, and this dataset is a very simple dataset with 18,000 restaurants. What we are doing here is just building the naive lexical search, very boring. We have this 18,000 restaurant menu items. We build this index and run the search. And what it is like very simple. You create a dataset. It can run on your local file system, or it can run on your own S3 or managed by us. You create 3 columns: restaurant name, restaurant review, owner answer. And all of them you specify that, hey, I need an inverted index. What's happening behind the scenes, you load all the data, you add the data to the dataset, nothing fancy. You get a dataset object that now has an index. And what it can do, it can run a simple query here, which says, hey, select all where this restaurant review contains this word and give me the top 4 results. And you get the answers. So far, so good. I think you have seen this all, nothing fancy. Now, what we are doing here is saying, okay, this is great, work it on local file system. What if I want to move this to the object storage layer? So instead, the only difference you should do is when you create the dataset, you point to your own S3, or you can also point to Activeloop storage, which redirects to your own cloud storage on Azure or GCS or on AWS. And then you can do the same operations, but now instead of inverted index, we use BM25 index and create a dataset now that can do lexical search. But the biggest difference here is that the index itself is sitting or residing near the object storage, which later helps you with cutting a lot of cost efficiencies, getting a lot of cost efficiencies when you run at scale. So far, so good. So let's go to vector search. Now, as you have seen, BM25, super easy. Currently, we add OpenAI, add the embedding function or define it, add the OpenAI API keys. And what here we can do is we create the same data set, but now we have additional column, which is the embedding. And the embedding, we define the type. That here's the embedding. We use their latest version of embedding model using the large one, and now define the data set. And when you commit the data, which happens here, the index is automatically created behind the scenes. And now you have this table representation of the dataset with 18,000 elements, and you can run both vector search and BM25 search at the same time on the same data. So here, we just define the type of the query we are running, define the query itself, and run just the vector search and get the top 10 results. And great, awesome, now we have the results. I think you have all seen this. I will not surprise you with any of this. Let's just skip. Okay, awesome. Now, how we can do hybrid search. Hybrid search is basically you run both queries at the same time, vector search and BM25 search, and then you fuse it. I think here's the vector search, here's the BM25 search. You run them separately in this case, get the final results for BM25 and vector search results. And the question is, what is the best way to fuse this? One naive way, you can take both scores, you sum them together, and great, you have a result. However, this approach is pretty bad because the way BM25 is doing the ranking process and returning the scores versus how vector search is working, they're very different. And BM25 is also very local. So if you just linearly sum them or with some coefficients, that's actually a pretty bad idea. What you can do, here, there's like a fusion you can define, which called, in this case, I use just softmax function. So we take the vector search scores, we apply the softmax function, and then the same kind of normalize the BM25 results. And then at the end of the day, we get these two results kind of merged together, which gives us the documents for both of those. Here's the merging, the fusion is happening here, where you take both the vector search, BM25, you normalize them, then apply some coefficients and sum them together, and great, you have now the final results returned to you. Okay, so far I hope I haven't yet surprised you. These are just standard methods. I think there's one thing interesting you can do with DeepLake very easily is that what I've shown you, everything the Python code was running in sync mode, you can just swap it to async, and it makes it easier to bring it to your Flask or Fast API application behind the scenes. And then now you can run both BM25 and vector search in async mode, get the results, and bring it back down to your place. Okay, so I think the key interesting stuff happens here is that when we want not only to run the search across a bunch of text documents, but also images. How do we do this? So again, now with use Clip. Clip is deep learning model, I think a couple of years ago, that can both embed images and text together in the same embedding space. And the way it's trained into, you have this image text pairs, you get the text encoder and image encoder, and then eventually you have a transformer that processes this data and gives you a vector representation. And you can use text vectors and search across image vectors, or you can use image vectors and then search across text data. And here we just use torch and clip to be able to load the model. Then the pre-processing function, we define the transformation that you have to do the images before you give it to the model. Now redefine the embedding function that can now process images on your own GPU. And get the scraped already data set we have, but you can scrape yourself. Image the data itself, and now define the data set. And now we have an additional column here, which is this types images where we add, and also the embeddings that we collect from the images themselves. Awesome, bunch of boilerplate code. And here's the search. The same way as you run the vector search, you can also run on the images themselves. And finally, get a result of here's the image query or burgers. We have a bunch of images inside the data set, run the query, and finally get a bunch of burgers back. Okay, so far so good. I hopefully kind of ramped you up to what is happening inside the search for the last maybe 10 or 20 years. And recently, there's new models that will help. Is what they did. The key innovation here is the following: is that instead of taking a single vector from a text passage or let's say images, what if we go and take vector per each token? The density of the data becomes very high and becomes very complex to manage. But what it can help is we can actually increase the accuracy of the search and the representation itself. So ColBERT, also done by Omar, so he took this approach, created this very dense representation of both queries and documents, and also defined this maximum operator where you can run a search across the text data. Currently, ColBERT is mostly used as a re-ranker, so I wouldn't be kind of using this for the main storage. But this gave this basis for building multimodal search without the OCR pipelines. And this is where ColPali comes into the picture. Here we have now ColPali, which is an extension of ColBERT that can take the visual language model, the images, and give you this dense representation. And the biggest difference that you get is that now your OCR, the document itself, there's no new OCR pipeline used. The OCR pipeline has been replaced by a visual language model. And the good news is that only recently, a couple months ago, that the accuracy of the text search on ColPali became almost equal as if you parse this to a traditional classical OCR pipeline and get the vectors and then run the search. But additionally, what you can do, you can now also search across the figures or tables, which haven't been possible to do before. The advantage is that if, let's say, you wrote, like, you have, let's say, 1 million invoices that are coming to you, you have built your like OCR pipeline that works, and then there's a new type of an invoice that comes. Now you have to build this additional use case, which is not possible. Okay, so here we load the visual language model, have the preprocessor pipeline ready, and then we define the data set. We get the images from the following scrape data set, define the columns. We have the image, the question, the embeddings, and then here everything is the same as I showed you before. And then now we append the data. And during this appending process, we take the images, give this to the model. We get the bag of embeddings or this matrix of embeddings. And then now we, instead of embedding as giving a single vector, now we give a bag of vectors per each image. And finally, what you can build is this kind of chat with images use case where first you get the query embedding given a question. You take this query embedding and give this now, instead of using vector search, you use this maximum operator and get the most top 10 relevant images in this case. And finally, after retrieving the top most similar images, which is here is a figure example, you can give this to a visual language model to process or analyze this to be able to answer a question for you. And here's a representation of, I think, using OpenAI GPT-4o Mini for processing the image that was retrieved from the DeepLake dataset to bring it back to you. Finally, you get the image, and the answer was the question to it. Okay, how are we doing in terms of timing? We are getting there. So this is what I showed you now, is it actually the coding implementation of this left part, where you can go from Lexical, like the naive search, to image vector search, to later bag of embeddings, and then combine this all together into your agentic iteration search to have like a perplexity style answer engine. If there are 3 things I want you to remember about us, is that we are multimodal, we are 10x more efficient than any other database, and we are AI search ready, and this technology is already deployed in Fortune 500 enterprises across all major cloud providers. Thank you very much. Well, I think it's any other language model. It will work for generic use cases that has been trained on. But if you have very specific use cases, you have to go and fine-tune yourself. The best way is to check what ColPali dataset has been trained on and see if your data that you use in enterprise is trained on this or not. And if not, you can actually take that and fine-tune for your use case and improve it. I think you asked another question actually in the beginning, not just about the model distribution, but also how the ColPali, I guess, works, right? And it's very similar. What we are going through is very similar to like there's another technique you mentioned, which is late chunking. And what late chunking does is like, hey, instead of us feature engineering the first chunking process, what if we delay this later and then we can figure out the chunking after the embeddings are happening and then find the relevant chunk or the context. And what it all goes into is like, if you think of embedding the data, which is your perception model, and then you have these agentic iterations, which is your planning model in self-driving cars. And they are now like manually feature engineered together. And then we are like kind of approaching this process where everything will be end-to-end neural network. And the way you're going to train these models is, hey, here are my question, here's my data set, here's my questions, and the labels and the answers. Can you actually fine-tune the whole end-to-end system to be able to answer this question? And as you go into get more data, as you get into more production, as you get more miles out of your system and cover all the edge cases, you will figure out, hey, fine-tuning every part will improve my overall accuracy. And this is what like Tesla Autopilot team is doing every day by collecting all the data and retraining their models and deploying them in production. Yeah, I didn't talk much about this second part. This is how agentic iterations should be implemented. But yeah, so there's like, you should take a combination of text to SQL plus the vector search, lexical search. So you kind of use all this combo of techniques currently, but step by step, all this will be removed. And the hope or the vision is that everything will become into a neural network where you no longer will need to be able to like manually feature engineer all these sub techniques. not now. Will take us years. We were promised.
It's tough.
Yeah, we were promised self-driving cars like 5 years ago, so it will take time. So we have one of the Bayer, which is a life science pharma company. They have a lot of radiology images. We have Flagship Pioneering. They have a lot of scientific articles or do search on PubMed documents. We have Matterport as a customer, using what they do. They do 3D reconstructions of real estate, where we go to Zillow or Redfin. Whenever we do this 3D virtual scenes, most likely it's them running behind the scenes. We help them to manage the data for training their GenAI models. So those are some of the use cases that DeepLake is being currently used on. And we also have startups. They analyze all the YouTube videos, run search, and bring back the to be able to predict which video is going to go viral. And yeah, so that's kind of the specter is pretty big.